In the present lecture series, we are going to look at the topic of aerospace propulsion. In the aerospace propulsion part, next, that is, we are going to spend around 20 to 30 lectures. How are we going to estimate your performance of the gas turbine? That is in terms of ideal cycle based assumptions and ideal cycle assumption with losses. That is, if you look at that, okay, in the ideal cycle analysis, we are going to look at that the flow through your intake, flow through your compressor, flow through your turbine, propelling nozzle and all, isentropic compression and isentropic expansion. Even in the combustion chamber, we are going to have a constant pressure heat addition. But in the real sense, it's not going to be the case. So we have to treat it as both your intake and compressor, adiabatic compression, and you have to consider how much amount of pressure loss is going to be there in the combustion chamber also, you have to consider that. And even in the turbine and the propelling nozzle, we have to treat the flow as an adiabatic expansive process. And we are going to extend it to, first we look at the turbojet with afterburner and turbofan. So here we are going to propose a generalized thermodynamics aspect, that is by looking at each and every component of that, of your gas turbine engine, and we are going to collate together depending on your series of components, whether it's a turbojet or a turbojet with afterburner or a turbofan or a turbofan with afterburner. So we are ramjet engine. We are going to collate the component in the order and we are going to estimate the performance of the particular engine. So we are first session of lectures, we are going to mainly focus on the individual component efficiencies. And how are we going to get your state variables in the inlet to the particular component or outlet to the particular component. From the unknown state variables and flow variables, we are going to get the unknown variables from the known variables. That's a focus on that. And afterwards, we are going to focus on your turbo machinery and your combustion chamber in detail. So, some 10 to 15 lectures, we are going to focus on the performance analysis of the gas turbine. In the performance analysis of the gas turbine, we set a general objective as estimate the performance parameter such as your thrust, specific fuel consumption, propulsion efficiency, thermal efficiency, and fuel to air ratio for a various operating parameters such as your operating Mach number, operating altitude, your compressor pressure ratio, and turbine inlet temperature. So here what are we going to do is, we are going to assume your component efficiencies, isotropic efficiency or polytropic efficiency, we are going to assume that. We will look at that, what do you mean by isotropic efficiency, polytropic efficiency in the coming lectures. So we see that general objective. So we are going to segregate the general objective into a multiple specific objectives. First is, we are going to look at that, understand the thermodynamics and fluid flow behavior associated with each and every component of the gas turbine engine. Apply the fundamental understanding of thermodynamics and fluid flow behavior to arrive at the performance behavior of each and every component of the gas turbine in terms of stagnation pressure, stagnation temperature, and fluid flow velocity if necessary from the assumed component efficiencies, and estimates the performance parameter of the gas turbine engine using individual component performance behavior. We know that how the engine is going to be part of the components. So first is, I have taken your schematic diagram of a simple turbojet engine. Simple turbojet engine. This is the operating cycle of that simple turbojet engine, whatever the engine I had given. You know that, okay, it's a basically ideal cycle with losses, Brayton cycle. You know that your operating cycle is going to be your Brayton cycle. What do you mean by your Brayton cycle? It's a constant pressure cycle. Constant pressure heat additions. or we will simply say that constant pressure cycle. So if you look at that, this TS diagram, it's nothing but your ideal cycle with losses. Ideal cycle with losses. You look at that, A to 1 is going to be your intake, 1 to 2 is compressor, and 2 to 3 is combustion chamber, and 3 to 4 is turbine, and 4 to 5 is a nozzle. So here, why did I say that with losses? If you look at that, whether A to 1 or a 1 to 2, it's not an isentropic process, because this is a S entropy, this is a your temperature. Okay, the entropy is not a constant, but it's an adiabatic compressor in the case of your intake. In the case of your intake here, and adiabatic compressor. But in the case of your ideal cycle, what is going to be in the case of ideal cycle? It's going to be an isentropic compressor. In the case of an ideal cycle. Same way in the case of your compressor, if you look at that 1 to 2, it's going to be an adiabatic compression again. In the case of your ideal cycle, it's going to be an isentropic compression. Okay. So, in the case of your ideal cycle assumption. So, if you look at that, the A to 1, that is in the intake, what is happening? Whatever the incoming air kinetic energy is converted as a pressure energy. Kinetic energy is converted as a pressure energy. If you look at that, the area of that your intake portion, if you look at that clearly, if you look at that here, you can see a diverging area. So what will happen in the case here? In the case of a diverging section, your velocity is going to decrease across your this one. Your velocity is going to come down. Your pressure is going to increase. That is, your static pressure is going to increase. Okay. So next is in the case of a compressor, there will be two types of compressor will be there. Your centrifugal compressor. Another is your axial compressor. So basically here, modern day gas turbine engines, they are using a axial compressor extensively. Here you are going to have a rotor plus a stator. So basically a combination of rotor and stator is called as a stage, one stage. So in the case of your rotor, what is happening is, the kinetic energy of the incoming fluid is going to be increased. Fluid is increased. In the case of the stator, whatever the increased kinetic energy is converted as a pressure energy. In the case of your increased kinetic energy is converted as a pressure energy. Depending on your requirement, pressure ratio requirement, the number of stages will be depending on the pressure requirement, pressure ratio requirement, compressor pressure ratio requirement, the number of stages will go up. Increase. Okay. So we'll go after completing your performance of your gas turbine and ramjet engine. We'll go in detail about turbomachinery, thermodynamics of turbomachinery. There we'll talk about that, how to draw velocity triangle, how to design your axial compressor, centrifugal compressor, those things and all. We are going to look at that in detail. Right now we will go to the next component of that. After that, your compressor, you are going to have a combustion chamber. In the combustion chamber, what is happening is, okay, in the case of ideal sense, your constant pressure heat addition. That's what the essence of your Brayton cycle. But if you look at that your combustion chamber, okay, because of fuel air mixing, fuel to air mixing, and flame stabilization process, and flame tube cooling process, there will be a pressure loss. Okay, so that we have to consider. Accordingly, you have to give a pressure correction for that. Whatever the pressure coming out of the compressor, okay, how you have to, normally they'll be taking something close to 4%, 3%, 4%, 5% will be the pressure loss of your compressor delivery pressure. That's what they used to say, compressor delivery pressure. Okay, you should be, you know how to calculate that one. So what is happening in the case of your combustion chamber? Okay, your air is going to be enter into that. Okay, it's T02. Okay, CPA, and you are going to add the fuel here, and you are going to get m dot A plus m dot F, your CPG, because hot gas, and temperature is going to be T03. So you are going to increase the heat energy in the case of your combustion chamber by burning the fuel in the air. So there your fuel is going to react with the oxygen. Okay, for example, methane as a fuel. Okay, if it is going to be reacting with your O2 that is present in the air, O2 plus 79 by 21 N2. This is a molecular formula of your air. Okay, it's going to give in the complete combustion, it's going to give the CO2 and H2O in the case of your complete combustion. But whether it's happening in and all, it's really a big question. Okay, modern day combustion chamber, we are working towards to achieve a 100% complete combustion. While going for the component performance, we will be looking at that in detail about all those things. And here we have to look at that your equivalence ratio, lean mixer, rich mixer. Okay, and your theoretical air, excess air percentage, how are we getting your adiabatic flame temperature, those things and all, we will be looking at that in the case of your combustion chamber. Okay, right now next is we will move to the your turbine. Okay, in the turbine your axial turbine will be there. Okay, so here whatever the hot gas that is expanding through the your turbine, coming out of the your combustion chamber, expanding through the turbine, and that's going to provide your work output, your soft work. So if you look at that, if you see that your previous diagram, you see that this is your compressor. Okay, this is your turbine. So they are connected by means of single shaft. Whatever the hot gas expanding over the turbine, they are going to have rotate it. Your turbine is going to rotate, and because of that your compressor is going to rotate. That's what is going to happen. So initially at the time of starting your gas turbine engine, you need to provide a power to your engine to rotate the compressor. Then after some time a self-sustained motion will be there. Even if you look at that, if you are designing a gas turbine engine, the main challenging work is going to be matching up the compressor and turbine. We will look at that in detail. So next is your turbine. Afterwards your propelling nozzle. Okay. So in the propelling nozzle, whatever the hot gas that is coming out of your turbine, they are going to be expanded through that your propelling nozzle. If you look at that, most of the gas turbine engines, so they are going to have a conversion nozzle. Okay. So even while going for the conversion nozzle, okay, even you might have studied in your compressor flow course and all convergent divergent nozzle. But why we should not use a convergent divergent nozzle, why we have to use a convergent nozzle here and all, we will look at that in detail. Okay, so here the area is going to be converging area. So whatever the thermal energy, pressure energy that is available with the whatever the gas coming out of your turbine is going to be converted as your kinetic energy here. Kinetic energy is going to be increased. From that only we are going to generate a thrust. So we know that the thrust equations, okay. So that is going to be your m dot a plus m dot f into your VE minus m dot a into VA. Next one is your PE minus PA into AE. So what we call this one as a momentum thrust. What we call this one as your pressure thrust. Okay. So if your nozzle is going to be whatever your expanding gas, if it is P is equal to PA, you know that okay, your pressure thrust is going to be 0. This nozzle, what we call it as a correctly expanded. Even your P is equal to greater than PA, okay. So your pressure thrust is going to be positive, but this nozzle, what we call it as okay, under expanded nozzle. So here if you look at that the exit of the nozzle, you can see that expansion fan will form, okay. Expansion fan will form, okay. So they are going to reflect with the free boundary, okay. Unlike reflection, oblique, your expansion fan is going to reflect as a oblique arc, and your oblique arc is going to reflect as a expansion fan. Basically what we call it as a unlike reflection in the case of your free boundary. Unlike reflection, that is in the free boundary. In the case of your solid boundary, you are going to have a like reflection. If you look at that, okay, in the isolator, scramjet engine isolator and all, oblique arc is going to be reflected as a oblique arc only, okay. Here like reflection, okay. And next is phase, your PE is going to be less than PA. Here the nozzle is going to be over expanded nozzle. So here what will happen, at the exit of the nozzle you are going to see an oblique arc formation. Again, okay, because the boundary is a free boundary, you are going to have unlike reflection, your oblique arc is going to reflect as an expansion fan. So normally if you look at that, the exhaust coming out of your aircraft engine or in the rocket engine, you can see very clearly, you can see like a diamond like pattern at the exhaust. That's because of okay, this unlike reflection, your why it is happening and all, okay, for balancing the okay, your P is equal to PA, it has to convert at the end, whatever the energy coming out of that, it has to make. So for that you are having a successive reflection. We will be discussing that in detail in the case of your propelling nozzle area. So right now we look at that. Your m dot a is nothing but okay, mass flow rate of the air entering into that. M dot f is the fuel flow rate. And your V is the exhaust velocity. Your VA is your flight velocity. Okay. So this is the thing we have to understand. Your P is the exit pressure. PA is the atmospheric pressure prevailing at the particular altitude. If you would like to hear about our video updates regarding your gate preparation, subscribe our YouTube channel Chalian's Gate Academy. Kindly share our videos to your friends and peers. And if you have any questions or any suggestions, please write it in the comment column. Even if you have any technical queries, please write it on that. We will clarify that.